I'm really happy, delighted to the webinar of today to be presenting Professor Manel Baucells. Before, however, we jump into the scientific part of the webinar, just a few reminders. We have a dense agenda as a decisionalized society in the next weeks. First of all, May 1st is already an important deadline for the Informs 2021 annual meeting that will be in October. Our DAS chairs have sent out messages concerning the proposals for sessions, so for proposals of sessions that can be in the form of flash talks rather than a traditional session, or something they are inventing for this particular year. So please do not hesitate to reach out to me or to Jonathan and Eric, whom I thank a lot for their work, in case you wish to have proposals or you have ideas for the 2021 Informs annual meeting, so the decision analysis sessions in that meeting. Going in temporal order, May 20th will be our third DAS webinar with Professor Ian Chen of University of Michigan. So again, DAS agenda, so save the date. It's going to be a Thursday. The time is the same as the one that we have today. Then we have the important June 22nd, 23rd DAS Society for Risk Analysis Conference on Decision-Making on Emerging Risks. It's a virtual event that has been organized on our side by Cara Morgan, whom I thank a lot for her work and keeping a steady pace. We will be able to set up the registration website in a few days and send out the announcements. So enroll massively to this event. And then June 2022, we will be in Darden Business School, thanks to Yale, Grushka Cocaine, and Manel Baucells that are organizing the ADA 2022 Advances in Decision Analysis Conference. So that's all in terms of the announcements. Another service announcement I need to make, in case you forgot to renew your DAS membership or not a DAS member yet, please just do not forget to do it. And now we are at our scientific part. The title of the webinar is Utility of Risky Payoff Streams, but Manel will tell the title and everything better. Just a brief introduction. Professor Manel Baucells is now at Darden Business School. Before joining Darden, he was a full professor at Pompeu Fabra, worked at the REN Corporation at IESE Business School in Spain. He did his PhD under the supervisor of Steve Lippman and Lloyd Shapley, who was a 2012 Nobel Prize laureate in economics. He serves as department editor of management science and associate editor for operations research. And I will leave the floor to Professor Baucells to describe his research in this promising and very interesting webinar we are going to be part of. Thank you, Manel, for accepting our invitation, and I will immediately start sharing my screen.
Thank you, Emanuele, for inviting me. It's really an honor to be in the footsteps of David Bell. So today talk, actually, I'm gonna, some of previous work from David will come up here as well. So the title of the talk is Preferences over Risky Payoff Streams, Normative and Descriptive Approaches. I'm going to begin with the normative side, and then we'll transition to the descriptive side, which will build on top of the normative one. What do I have in mind? What I have in mind is an object like what you are seeing here, where at time zero, you will say invest $100. And then in period one with 50-50, you will get an additional 120 or 40, which will bring your profit to either plus 20 or minus 60. You will still not recover the investment in the second case. And then in period two, you will have an additional cash flow, which may depend on what happened in period one, as in this case, bring your total profit to 4 possibilities. Why is this domain important? Well, it's because, at least when it comes to just preferences over money, it's the most general that we can have. So it will have lotteries played today as a special case. It will have streams of cash flows under certainty as another special case. And it will have repeated lotteries as another special case. And it's relatively complex because you don't know whether you have to look at the cash flows or the profits. And we're going to see what type of preferences you should hold over these objects, both from a normative and a descriptive side. And then we will also learn what this preference structure imposes then on lotteries played today or on cash flows under certainty. For future reference, I'm going to introduce here what we call a profit profile, which is simply the probability distribution of your profit at different moments in time. For instance, if the world were to end at time 0, you will lose 100 with 100% chance. But if the world ends at time 1, then you will have a 50-50 chance of losing 60 or 20, the accumulated profit up to that point. And if you actually reach period 2, then your probability distribution is an equal chance of these 4 outcomes. I hope that this is clear, and we're going to worry about probability distributions over profits at different moments in time. So these are going to be like our object of choice. And now let's move to you guys. How do you feel about the following prospects? Again, use your intuition. Would you accept a 50-50 chance of losing $200 or winning 300 heads tails? I don't think we have an easy way to record the answers, but just think for yourself. How would you feel about this prospect? Next, we're going to do the usual thing of saying, well, what if instead of 1 coin, we throw 10 coins, and then you will lose $200 for every tail and make $300 for every head. And we're going to flip that now, the 10 coins now. Would you find that more acceptable? Would you like it? All right. Now, how about we do the following? We wait 10 weeks, and then we will throw the 10 coins then. But you have to tell me today if you want to do that or not. Would you accept that proposition? Okay. And now for the punchline, how about we are going to flip 1 coin per week? So every week we'll flip a coin. If it's heads, you'll make 300. If it's tails, you lose 200, and we'll do that for 10 weeks. And now I want you to tell me between condition 3 and condition 4 here, which one you like the most. I don't know if you want to put that on the chat so we can see it. Indifferent, 3, 4. Okay, yeah, 2 definitely is better, but if you can only choose between 3 and 4, looks like the floor is a bit divided here. Geez, we're talking about decision analyst. All right, so let's look at what happens. So there's a little bit of division between what's best. On the one hand, the risk profile is the same because you are flipping 10 coins and you get the same profit per head and tail. Sequential actually gets those payoffs sooner than if you just wait 10 weeks and you get the 10 coins. But some of you guys don't like the sequential, say, no, I'd rather wait and flip the 10 coins all at once. So let's look at some evidence. So this is a survey from my MBAs. Where I asked these 4 questions, play once versus nothing. And then here, the majority prefer not to play when it's only once. But I hope the notation becomes self-explanatory as we go. So this is going to be playing 10 times now. And then they say, oh, yes, if it's 10 times now, I will definitely do it. If it's 10 times in 10 weeks, they actually like it almost the same. A bit less, but almost the same. And then when we have the sequential version, which is denoted by this, they still want to play, but not as strongly. So then I point blank ask my MBA students, look, what do you prefer? Wait 10 weeks and then play the 10 repetitions, or sequentially play 1 repetition per week? And the majority prefer 3. So 3 So in this case, 3 will be better than 4, as some of you have also answered here. So that one question we'll answer today is that, is this rational or not, okay? So then without further ado, I'm gonna set up what we think are the standard rational axioms that apply to these profit profiles of what we have defined as the profit profiles. First axiom is you only care about profit profiles. So if two risky payoff streams produce the same probability distribution at each moment in time, you will be indifferent. Then you will have a complete and transitive preference. It will be continuous. It will satisfy the independence axiom. So if you mix a profile with two profiles and you mix them both with a third one, your preference should not change. You prefer more money to less. Then you are impatient. If something is good, you rather have it sooner. And if something is bad, you rather have it later. And then weak stationarity, like that will be our choice 2 versus 3. So if you prefer 10 repetitions now, and then I do the 10 repetitions in 10 weeks, you prefer it equally well. So if something is good and you put it in the future, it's still good. All right, so ready for the representation then. So here is the result. A preference satisfies these axioms if and only if there is a utility over outcomes and a time discount function over time, such that your preference is the discounted, expected, incremental utility. So you will take utility of the profits up to time t minus the utility of the profits before time t up to the previous period, and you will be taking the expectation of that difference. So this model, we'll see in a moment that it's the theory form is not entirely new, but it has not been used much. So in that sense, it's up for grabs, like to develop any application of this. Of course, if you strengthen the axiom 6 to stronger stationarity, then you will get exponential discounting, or if you impose dynamic consistency. So if you want a fully like normative model, you can just set S of t equals to E2 minus rho t for some discount rate. One interesting thing about this model is that you can derive it heuristically, not based on axioms, if you just take the notion that time is inherently uncertain. This is the notion that your time discount function, which is that the decreasing function could be an exponential decrease or something else, it's interpreted as a subjective probability of making it to period t. So there's a chance that time will end. Again, this is an interpretation. It's a heuristic way to derive the model. The model stands by itself on the axioms. But if you just think of time as something that is inherently uncertain, then what you would have is that S of t is the probability of making it to time t. Then here on the left, this will be the chance that I don't reach period 1. 1 minus S of 1 is the chance of actually not reaching period 1, which means I will end up losing the 100 in the original cash flow example. Then S of 1 minus S of 2 will be the chance of reaching period 1, but not 2, and so on. And then these at the end will be the chance of reaching the terminal period t. So the vertical axis that goes from 0 to 1 can be interpreted as a probability of making it up to different time periods. And then what you would have is the probability of reaching terminating at every individual period times the consequence, which will be the expected utility of the profit up to that time. So if you think this way, and then you work out this expression, you will get back the equation 1 that we saw in the representation before. So it's really a nice result. As you will see, this time as inherently uncertain is a nice way to think about time, and this model captures that. Okay, then important historical note, the utility form that I just axiomatized was proposed by Bell in 1974. And many of you may not know that. Not based on axioms or the notion that time is inherently uncertain, at least in the paper doesn't mention that, but just on the observations that these two payoffs are receiving nearby times, then their utility should be similar to that of receiving their sum at once. So if you just work with that assumption, you will also get to that model, which is another nice property to have. And then Bell paper has been cited only 37 times, and equation has other equations, but equation 4 that has the incremental utility has been used 0 times. As far as I trace all the citations, and nobody uses the incremental form, so there is plenty of opportunity to have novelty on that end. So I'm going to try to advocate for what that form means, why is it different, and what are some opportunities to develop this incremental utility approach. Well, first of all, what are special cases of the model? Well, 2 trivial ones are discounted expected payoffs, which we all use. So just put U linear, and then the cumulative payoffs will cancel out except the current payoff, and you will just get discounted expected payoffs. And also, if you are perfectly patient, then you only make it to time t, and then you get expected utility of final profits, which is the baseline model in many finance papers. And let's say the derivations of the capital asset pricing model are based on that initial assumption. And here is one novel model that I really love. It's discounted Kelly criterion. So if you take utility to be the logarithm of some initial play capital plus your current profit or your current cash flow, so here C minus 1 will be initial capital that you're willing to put at risk. Then you define the cumulative capital as your profit plus this initial level. And then the utility differences that we saw before just become the logarithm of the ratio of your current capital divided by the previous capital, which is the Kelly's criterion. So then what you get is the discounted Kelly criterion. So that I don't think anybody has worked out what this means, let's say, for portfolio theory. If it will give something novel or not, I don't know. But again, it's an opportunity to work with a completely rational novel model. Okay. So here is another example of how this model differs from the standard one. Imagine an investment, X0, some negative amount you have to put up today, hoping that in some time in the future, you will receive a positive payoff that may or may not offset your initial investment. Then if you apply the incremental utility model, in this case, you will get 2 terms. One is the usual expected utility of final profit, plus another term, which will be the fear of losing the initial investment. And think of this, like imagine I make the initial investment bigger, so you have to put up more money, but then I make the cash flow at time t also bigger by the same amount. In theory, if you all care about a utility of final payoff, you should be completely different to that move. But I think that rationally it's okay to be worried about this delta getting bigger, because what if I don't make it to time t? And that will rationalize that lack of preference over increasing delta. You would not like that. Okay, it's also interesting to see what are the models excluded. And a model that's excluded is the time separable model, which is tempting to use, but it's really not very good. And the reasons are, first, if utility is strictly concave, it treats payoffs as complements, even if they are receiving nearby time. So this is a theoretically flawed model in that regard. But then also, if you add serial correlation to payoffs, this model will be indifferent to serial correlation, but actual subjects and rational subjects will not be. So they will definitely respond. If the second coin is correlated with the first heavily, they will change. It will change their preference for sure. And then here is the interesting descriptive special case. When you think of U as a standard loss-averse utility, just to make it simple, imagine it's piecewise linear, like U of X is X for gains and U of X is lambda X for losses, just a loss-averse utility over the status quo, let's say 0. What this model will tell you then is that first of all, if you are on the gains portion, you will be using discounted expected payoffs, no problem. But if the cumulative payoffs become negative, then a positive payoff becomes a very a much welcome reduction of a past loss. So in that sense, it counts twice as much. So if I had imagine you invest in the stock market and you start losing money, then all of a sudden you make money. That money will actually count lambda times the gain because it reduces a past loss. And similarly, if you have past gains, then a negative payoff will not be a loss, will actually be a lesser gain. Unless you're in the red, then it will be a bigger loss. So I think that it's very, sounds very realistic, and that will be the key application from a descriptive viewpoint of this model. And now back to Summation Paradox and to the coins that we flipped. So we have this general result for model 1. So assume you have 2 or more repetitions, and that the risk profile of every repetition and your utility is such that n repetitions today are acceptable, but less than n repetitions are not. So suppose you are on that age that say, well, I need about 10 repetitions to like this, but less than 8 or 7, I would not like it. So if you are in that case, then model 1 will say that simultaneous delayed play is strictly preferred to sequential play. So those that answer 3 would have been follow the model if they also rejected the single play or close to up to 10 repetitions. In contrast, if all repetitions are acceptable, so you say, oh, you like 1 play, 2 plays, 3 plays, this is positive expected value, I don't mind, then sequential play should be preferred. So that will be the idea. So in other words, the sequential versus delayed simultaneous in this model goes hand in hand with Summation paradox of liking several repetitions but not liking 1 repetition. Of course, if you are in a totally normative setup and your utility is a smooth function over wealth, then Pratt and Zeckhauser argued that if n repetitions are acceptable, then less should also be acceptable. So in theory, the rational thing here will be to also like sequential over delayed simultaneous. But if you are loss averse or you don't like single play, then this model would say that you will also not like sequential. You will prefer delayed simultaneous. So I think that's a nice result that's completely general from that model and gives like the temporal version of Summation's paradox. And now we move to, so this is it for the rational part of the presentation, the normative aspect of the model. Now we're going to move towards more completely behavioral. So not only we're going to have U to be a loss averse value function, we'll try to incorporate, if you will, nonlinear probability weighting or something to that effect, you will see. So I've been teaching for 3 years now a course at Darden, behavioral decision making, where I introduce students to loss aversion, decision weights, decreasing impatience, magnitude effects, mental accounting, and all that. And the feedback is positive, but not all of it. So let me give you a couple of feedbacks that I got this last time. One student said, combining loss aversion, time discounting, and the other factors will be a great review and takeaway for the course, like put everything together. And another student said, by the end of the course, it started to get a little confusing how all the different models interact with one another. And the fact is they are completely right. The idea is that behavioral models are piecemeal. You have prospect theory for things that only pay once, either now or later, but only one payment time. Or you have hyperbolic discounting for cash flows under certainty. But if you combine risk and time, like we're doing here with these risky payoff streams, it's very unclear how the full prospect theory will carry into our setup. What to do with decision weights here specifically. So that's what we're going to attempt to solve. And it may not be a satisfactory resolution, it may be, but at least it's something that I've been thinking for many years now. And the resolution is kind of surprising. So as you will see, rank-dependent models and prospect theory in particular do not generalize very well to more than 2 outcomes, and then you need a different way of looking at things. So let's see how that goes. So the starting point here is the paper that Franz Heukem and I wrote in 2012 called Probability and Time Trade-off, where we carry this idea that time is inherently uncertain. And then we thought, well, if you receive at time t a gain g with probability p, this is going to be encoded as a chance of s of t of making it to time t and one of s of t of not. And then if you make it to time t, then you will play this lottery. And if then you apply prospect theory to that, you will get the weighting function of the probability of the outcome, which is the composition of the chance of reaching time t times the probability of p, and then the utility of g. So that was the model for a very simple setup, and it integrates really prospect theory and time in a nice way. And this is descriptively quite appealing, this form as well. But how to generalize this to more than 2 outcomes? It was an open question. Okay, so that's what we're going to try to solve today. So, and here will be the idea. So now the prospect I'm going to use is the following: is at time 0 you invest L, that may be a potential loss, and then at a later time t bigger or equal than 0, with probability p you will have a total profit of g, and that means that you will have a cash flow of g minus L, bringing your total profit to g. That with probability p you will end up with a profit of g. And with 1 minus p, your cash flow at time t will be 0, in which case your total profit will be L, a negative number. So this is it only has 2 possible outcomes at time t, g and L, and then at time 0 you may lose with L. And then, as we argued before, the incremental utility model will give you this expression. It will be S of t, it will be the expected utility discounting with discounting. That will be the model. So you have the fear of losing the initial investment plus the expected profit at time t. Now, what we would like to do is to gain descriptive appeal by adding the notion of nonlinear probability weighting. And we're going to do that here. So this is a heuristic modification of the previous model to make it behaviorally more appealing. Why do we like equation 4? Because if you set time to 0, then you will get the biseparable model, W of P U of G plus 1 minus W of P U of L. This model is at the intersection of many behavioral models, including cumulative prospect theory, but many others, and it's behaviorally very robust. So if your model does not particularize to the biseparable model for 2 outcomes, you're already like in the wrong footing. And then for L equals 0, it becomes the PTD model that I just showed you in the previous slide. So this is what we want. So this function. Now the challenge is, how do you extend 4 to more than 2 consequences? Now, if you try to extend 4 using rank-dependent principles, what you get is a complex and an appealing expression. Because now if you treat time as intrinsically uncertain, then you get like a strange combinations of S of t's and actual probabilities that it's not very appealing. So what we're going to do instead is rewrite 4 as, that takes like 5 minutes of algebra, but you can move U of L to the left, then divide by U of G minus U of L, then take W minus 1 on both sides, and you will able to write equation 4 like this. Well, that's just algebra. But now let's just start thinking. We're going to define D as the inverse of W as a range distortion function, because what's inside this D function is a normalization of the outcomes relative to the worst and the best. So you will take like the normalized utility. So now 1 is the best outcome, 0 is the worst outcome in utility terms. And then you will also then define explicitly a range utility function like this, which will be first you normalize your all utility, and then you apply the range distortion D to that. And then equation 4 can be written like that, because U bar of G, that will be 1, and that will be 0. So that trivially becomes S of T times P, and the left-hand side is D of U of the normalized certainty equivalent. But once you have that, you realize that this is just what the normative model will do, except that you're using U bar instead of U. So you're using a range distorted utility instead of your utility. But other than that, you apply the model that we saw before. And this is the idea to go in this direction. The range distortion function D, right, if you are familiarized with prospect theory, you can think of this as the inverse of W, so that if W is inverse S-shape, then D will be S-shape, like S-shaped curve. It captures Perducci's range principle. Perducci argued that people have a sense of large and small given by the context, and that they will normalize outcomes relative to the range. And then there's recent neurobiological evidence that people, the next slide will show you some of that the function is S-shaped. In our particular axioms will actually make it symmetric, so D of 0.5 has to be 0.5. And then intuitively what D does is it magnifies the center of the range as a lens, and then makes the extremes of the range less sensitive to that. And then a simple parametric form is just to invert the Gonzalez and Wu weighting function. So that will be something that if you assume gamma bigger than 1 here, you'll have an S-shape, and that will be the inverse of that. Here is some neurobiological evidence when you change make the reward amounts more close to each other versus you make them more separate, then you can, the neural response is more sensitive in the middle, but relative to the range. So if you have a narrow range, you will have an S-curve that's steeper. If you have a wider range, you will have a flatter S-curve. And this has to be like that, because your neurons can only transmit within a range of 0 to 100 action potentials per second, I believe. So then if the output range is the same, you have to normalize the inputs so they always fit into the output range. So it's very well established in this type of range distortion or normalization. And then there's a set of axioms, B1 to B9, that I'm not showing. They are on the paper. And by the way, I'm gonna make the paper available on the chat so you can look at what we are, at the axioms in particular, where we show that a relaxed version of the previous axioms make them range dependent will be represented by a utility function as before. Then the time discount function could be range dependent, and then a range distortion function D, so that your utility will be as before, but with U being replaced by U bar, which U bar is given by the distorted, range distorted utility. Well, what you have in front maybe I don't know if it's going to stand the test of time or people will use it or not, but at least is a behavioral model that has the full domain of risky payoff streams as domain. So that it will make predictions over these very complex objects, and in that sense, none of the existing models have this generality, so they cannot. At this moment, I don't think this has competition because there is no. Or somebody says about the temporal problem. Well, throughout this presentation, we're assuming that the individual only worries about reception times. They are indifferent to resolution times. So throughout this presentation, we and we are doing utility over money. So we are not thinking about consumption. So it's just utility over money. But that has the advantage that you could think of this sum of payoffs, then you could think of that as sum of instant utility that you may get from consumption. So then you could translate that into a consumption model. But that for today, we're staying with payoffs and only worried about reception times. And we are indifferent to varying the resolution time. Okay. So this model, it's difficult to see from this expression what it implies. And let me just tease out some of the applications. So one is the range LG, we are going to be assuming that it's given by the context, by the menu of choices you have in front. So L is the worst that can happen from all the possibilities you have, and G is the best that can happen from all the alternatives that you have. In this case, then you will have context effects, because by evaluating an object by itself, that will have its own range. But if you compare it to something else that has, let's say, a wider range, then you may see the first object differently. And this is what has been observed and what also the model predicts. And then the nice thing is that the same mathematics work for risk and time. So if you have the preference reversal, you have the dollar bet, you will have, it will be $9 with probability 30% to be received now. So this is XPT. And this will be $4 with 70% to be received now. And then what's found is that the certainty equivalent of the dollar bet is bigger than the certainty equivalent of the P bet, which in our model that will imply these equations. But then when you compare side by side, you find that the P bet is preferred to the dollar bet, which in our model will have those equations. Can those two inequalities hold together? And the answer is yes. If D has a decreasing elasticity, then you will have that D of Z1 times Z2 will be less than D of Z1 than D of Z2. So an S-shaped function will typically have decreasing elasticity, and then we'll have that under proportionality. And then you will, no, I think I have done it the other way around. So we will have the D of the product, we want that to be sorry. Well, we're talking with actually the inequality was right, but here we're dealing with D minus 1. So when it comes to the weighting function, we'd have that the weighting function is subproportional. So D of P plus Q will be W of P, W of Q, and then D, which is the inverse, will be the other way around. But here we're talking D minus 1. So this is the one that we want, and it will then predict that inequality. And then when it comes to time, you can think Tversky, Slavic, and Kahneman then used the $6 with 100 to be received with 100% probability in period 8, or $4 with 100% probability to receive in period 3. And then again, they observed that the certainty equivalent of the L bet was bigger than the S bet, but that side by side, the S bet was preferred to the L bet. And then the equations are just parallel to the previous one. And you will also predict the preference reversal 4 times. So that comes very naturally out of this model. Something also, second one that it will appear is the following. First of all, if the discount rate defined as the rate at which your discount function decreases is constant or decreasing, that's the usual pattern being found of decreasing impatience. That means you are very impatient in nearby times, but then you become progressively more patient in the far future. So if your parameter, if your discount rate of the representation is decreasing, then you will observe decreasing impatience, meaning that if you are indifferent between, let's say, 3 periods from now and 4 periods from now, and then I move those 2 payoffs sooner in time, you then will like the one that pays sooner because of decreasing impatience. And this we observe. So we observe these patterns. So that it's not surprising is what you would expect from a model. The surprise comes now. Rubinstein observes that if you pay both in period 2 and period 3, the 4, versus paying 5 also both in period 3 and 4, then the preference goes the other way around that you would have thought. That it's all of a sudden people become more patient when individually they were indifferent or prefer the sooner. Now when you put together, they prefer the later. This is a puzzling violation of decreasing impatience, and our model can explain it with D being a shape, because the general result we have is that if you're indifferent between the original 4 and 5 in period that we saw here, then your discount rate has to be decreasing, fine. The elasticity of U is decreasing, which is what's been usually found. It's usually constant, like power U or decreasing elasticity. And then the elasticity is increasing, but that's not the direction we are finding D. D tends to be decreasing. Then you will predict the normal thing, which will be you will have decreasing impatience. But the fact is you observe the opposite. So that means that one of those 3 has to fail. But discount rate cannot fail because we have seen this. This will be very surprising also, because utility tends to be constant or decreasing elasticity. So it has to be the case that this is decreasing. And that's what goes with the S shape. So this is just showing that this model has like a lot of behavioral appeal, and that extensions of the rank-dependent model will not be able to cope, for instance, with these late effects. So here are a variety of anomalies that could be explained: the 4-4 patterns for certainty equivalence in binary lotteries, the dislike for sequential versus preferred delay simultaneous, preference reversals, decreasing impatience and lack of decreasing impatience, and then magnitude effect in discountings because the function S could be range dependent. So I think that will be a good place to stop and take questions about either the normative side of the incremental discounted utility approach, or questions about this more descriptive approach to use range principles instead of rank principles to extend this model into a behavioral, in a way, to combining prospect theory and hyperbolic discounting, if you will, but it's not really that, because we are using range principles and not rank principles. All right.
Thank you very much, Manel, for this wonderful presentation. The floor is open to question and answers. I think you can activate your microphone and ask anyone who wants to start. We had some, okay, Luke, if you want to start.
Yes, I'm interested in the comparison you made with the simple sum of discounted utilities. And I wonder if there is an intermediary model where when two outcomes are more distant, you'd have some kind of a reset of the utility function, but when they are close, the increments would accumulate.
Right. Okay, so you want to go in the direction of making it even more complicated.
Yes.
Well, first of all, the model as is, it's already much more complicated than usual. So, and it has not been explored. But who knows? You could make it even more, add more behavioral features, if you will. One feature that right away you could add is adaptive reference points. Like currently your reference point is at 0, and you don't anticipate your reference point to change as time moves, which it's okay. But if the decision maker adapts the reference price and anticipates that adaptation, then you will have an even more complex model that will capture some of what you're saying, that maybe the increments are built differently as time moves.
Thank you.
Okay, I saw someone else raising hands. Please just ask your questions.
Okay, that's Ilya.
Hi.
I will chip in. Yeah, hi.
Hi,
So, again, maybe I missed something, but what would be like, purely sort of normative multi-attribute approach here? So in the following sense, that let's kind of first consider the situation under certainty, right? So the only thing that is changing is that, okay, there are different payoffs at different times. So then I should have some value function over that, right? And then once I add uncertainty, I should have sort of something like utility over NPV. So where exactly that diverges from that approach?
So you're talking about utility over other attributes, or NPV, discounting the cash flows?
No. Okay, no. So the first thing would be, I say, okay, let me consider this, the situation under certainty, right? So, okay, there is some payoff in period 1, payoff in period 2, 3, and so on. So one way to estimate it would be through discounted cash flow, but it's actually not necessarily like this. I might have something more complicated, right?
Right. The idea of discounting cash flows, well, here you could discount based on inflation, just to make money the same, period.
No, that's fine.
If
What
you
I'm
want
just trying to
discount,
say,
yeah.
No, what I'm trying to say is that how your axiomatic approach would differ from this when you say, okay, first of all, let me introduce value function that compares different payoffs, but under certainty, right? And then let me add to it some averaging across probabilities.
Right.
As I understand, that would be like pure normative approach, right? There is still a lot of.
We have not done that here, but that will be interesting, especially if instead of money, you talk about consumption. I think that will be the best.
But like, yeah,
so you have utility over consumption under certainty, and my thought will be that this will be just your sum of moment by moment utility that you will get from 0 to t under certainty, and that will be the one that you get before. And then this model would add risk aversion to that. These are my thinking for consumption, but
okay.
I don't know exactly the form it will take. In here we have done everything together, so we have not done preference under certainty and then adding risk aversion to that.
Okay. No, I thought again in like sort of similar to Savage or Neyman Morgenstern or whatever, right? So we would say, okay, these are outcomes that I care about, and then I have preferences under certainty, and then I have preference under uncertainty. And just to see, where they diverge from what you get and so on. Because exactly as you said, you put everything together, so it might be a little bit harder to see, where is exactly sort of what is going on. Yeah, okay. And then utility of NPV would be just a special case, right? When you say, okay, when I have multiple income or consumption stream, I evaluated, using just discounting.
Yeah, this will be utility
That's
of
not
wealth.
required.
What we will have here is your utility function will be some initial wealth that I call C1 plus X. So it will be some utility for wealth that will be your form, but then it will be the accumulated profit plus your initial wealth that you had, and but then you will do this incremental utility. That's
okay.
what.
Thanks. Sorry, I don't want to kind of take all airtime, and we can always talk later. Thanks.
That's fine. Thank you, Ilya. We have had in the chat a couple of other questions. I don't know if the ones who wrote them are still here and you want to ask them directly.
Okay, so I have, is W a function or a scalar? W is a function. So W will be an inverse shape function. And then D will be the inverse of W, which will be an S-shaped function. For those that know about prospect theory, W is known as the probability weighting function, usually inverse S-shape. But then here we work with the inverse and interpret it as a range distortion function.
Okay.
And then, so D does the opposite of the cumulative normal distribution, which, well, actually it will do, D will do like a cumulative probability distribution. So one candidate for D actually is the cumulative of a symmetric beta with parameters less than 1. Then it will be S-shaped. So the cumulative of the cumulative CDF of a distribution could be a candidate for D without particular probability, with no particular probability interpretation, just as the mathematical form. So it will be steeper in the middle and flatter in the ends.
Can I ask a question?
Yes.
Hi, Manel. This is David
David.
Budeska. So in your last slide, you show a variety of anomalies that your model can accommodate. And if I understood correctly, it's in every single case by imposing some restriction or a certain range of parameter that will accommodate them, right? So the question is, are the ranges for these anomalies consistent or inconsistent
Yes,
with
they
each other?
So if you assume like loss aversion 2.25, and then a reasonable, even exponential discounting, you don't have to, for many of those, you don't have to make it hyperbolic or anything, just exponential discounting. It will predict, so a single set of standard parameters will predict this variety of outcomes.
So in other words, that you are predicting all of them simultaneously.
Yeah, yes, it will be a joint prediction under a fixed set of experimentally sound parameter values.
I see. All right. Thank you.
Can I ask a question, Manel?
Yes, Sebastian.
Also, again, to the equation 1, which your model nests, so the discounted incremental utility, so that the math is clear. I just wonder, like, oh, you had it, yeah. I just wonder, like, how to interpret. So on the one hand, I consider accumulated profits, but then on the other hand, I do not consume. So how do I have utility like during the whole process if I don't do anything?
Well, this is a model to fit preferences over payoff streams. So you ask people, you propose individuals different investments or payoff situations, and then they declare their preferences over those. And this model is meant to represent those preferences. Now, your question is, well, should money itself be the source of preference, or it's what you spend that money on that is the source of preference?
I think the equation says that you don't spend, right? So you just accumulate. So I
this
wonder.
Money says you like money, it sooner is better, and then we don't care about what you spend it on. It's just that you act as if your preferences are represented by this function. Now, again, the next step, or an obvious step, is to extend this approach to consumption. I have done that myself under certainty, and we call it the Cessation Model. And it's similar to Bell, because what you would have is, you will have the discount of utility of some cessation level plus your current consumption minus the utility of some cessation level. And then that cessation level would be a decay, a stock with decay of past consumption. So if you have recently consumed, Y will be high. If you have not consumed for a long time, Y will be low, and that will increase your marginal utility. So we have worked a consumption version of that under certainty. The question will be to put the two together, or then derive the indirect utility for money from this more basic consumption model. But again, those are open questions, exactly how you carry these two, consumption and the certainty, and then you add risk to that. It's not what we have done today. Today was all about payoff streams and preferences over those.
Okay, you know, that's I understand, and I'm sure you do enough in this.
But that's those are the opportunities to think, well, how would that apply to if I think of X as a consumption? Will there be an additional utility for consumption under certainty, over which I have risk preferences taking this form?
Yeah, and just the last quick question. So in this equation one, you think of the xi tilde as prospects. I mean, or typically you think of them being as prospects, having gains and losses, and this U could be a piecewise linear or an S shape.
Right. The behavioral version of that model will be U of X will be equal to V of X minus R, right? So will be a value function relative to reference point that you can normalize to 0.
But you also think that this could be useful if you have like U concave and you think more of the xi tilde as gains only. So right. I just like applying.
The normative application will be exactly the last one that you said. U will be a smooth concave function, and it will be your prior wealth or your play capital that you are willing to put at risk plus the profits that you make. And that will be like the discounted Kelly criterion I have mentioned. So that will be more like this, where your utility takes some form like that, or some function of C minus 1 plus X. Then the advantage of logarithm is that this gets simplified, and then you just get a very nice utility function. But in general, you will get a utility for wealth. And then the descriptive side will be to have U to be a value function that has a kink at 0, and then that has the idea that a positive cash flow may either be countable if it offsets past losses, or just be an incremental gain otherwise. And also negative cash flow could be a lesser gain, not multiplied by lambda, if it adds to previous gain profits, positive profits, but will be then a loss if it maintains you in the red, and which I think it's quite appealing.
And you alluded to this, like adjusting like a reference point, you know, in this dynamic model. Sometimes you like
in the story I just told you, R will be fixed. Is the R that you have at time 0, and you will not anticipate that R to change, which is also what has been found, that even though the reference point does change, individuals do not predict that very well.
Is it sensible, like to just to take the equation 1 and just have RT deterministic?
Yes, but then that will be an exciting model, but it will not longer satisfy the axioms, because then this little u will depend on time through the reference point. But here is an example. Imagine you receive payoffs occasionally, so that your reference point fully adjusts to your current wealth by the time you receive the next payoff, correct? Then what will happen is that this term here, that's going to be your reference point at t, because you will have adjusted to that by the time you receive that cash flow. and this is going to be only xt plus the reference point. So then this whole thing will become v of xt. So if you receive payoffs only occasionally and you fully adjust to, you have received setting the reference point to that, and you anticipate that, then you get the separable model. That's another hidden thing here, but I didn't. The problem here is that it requires a lot of assumptions, that you anticipate adaptation and that payoffs happen occasionally. But then if you assume that your past profits are your reference point, you have adjusted to that, then the cumulative of the profit is just your reference point plus your current one, and then you will only have b of xt.
Okay, thank you very much.
Yeah.
Thank you all. I just ask if someone else wants to ask an additional question.
I think I have.
Yep.
Yeah.
Okay.
I would like to go back to the question raised by Sebastian. Why do we have the sums under the utility? So the thing is, imagine that you have an impatient guy who cares about time, but then imagine that it's equivalent to a perfectly patient guy, but who faces uncertainty of the uncertainty that he will not make it up to the capital T. So then basically the patient guy cares about the sums only, right? Because he is patient. So then all that matters to him are these partial sums. And this is basically the most intuitive story you can make to support these sums.
This is Michal Lewandowski, one of the co-authors of the paper. I thought the beginning was somebody trying to give me a hard time, which he is trying always, but anyway, so yeah, so I think that's the other way to look at this model, which is as a survival story. Like you fear that you will not make it to time t, and then this is the utility that you get if you make it to exactly time t, this expression here. And this will be the chance that you make it exactly to time t. And that will be another natural way to interpret that model, that time is inherently uncertain.
And then one more comment, then that the way we axiomatize the thing is to use the Anscombe-Naumann setup, in which this st minus st plus 1 basically becomes a subjective probability of a state that basically
Right.
the payoff is truncated.
This will be subjective probabilities. I guess we can see this here in the definition of an act. In Savage, you have the horse race, that for every outcome of the horse race, you get to play a different lottery. And those are here the horse race can have 3 outcomes. And then conditional on the horse race, you will either play the lottery now, time 1, or the time 2 lottery. And then basically our axioms are the Anscombe-Naumann, that it's you first have a linear structure based on the independence axiom. And then since you have not given probabilities to the time state, those appear as subjective. So first you will have termination time, and then you will play a different lottery depending on at what time you reach. So that will be the Anscombe-Naumann proof of ultimately this version of the model. So that's the one that we prove, and then we show it's equivalent to 1.
Mm-hmm.
All right. Well, thank you so much for attending, and I hope that it has stirred your thoughts about how to think when you receive more than one payment over time, which is very, very, very common, and then that neither standard normative models do justice to that setup. So we had to rediscover Bell's model. Hopefully, the number of usage will increase from infinity, from 0 to more than 0. And then also this framework allows to replace rank principles for range principles and create what I think is the first integrative model of both risk and time that really captures a a lot of phenomena. So I hope that you like it and you use it.
Thank you, Manel. Thank you all for participating. I don't think there are any further questions. So again, thank you, Manel, for this
So much.
seminar. Is there other questions? No, I don't know. So otherwise, we just adjourn to our next webinar, which is on May 20th. Thank you very much. Again, thank you, Manel, and thank you all for being here. See you in May.